Hello, welcome back. Today is our last section of Chapter 7. We are hitting up 7.6, Applications of Quadratic Functions. So, what we are going to attempt to do in this lesson is we're going to be analyzing the graphs of different functions and looking at them in context to different word problems. So what makes sense, what doesn't make sense, what do the points represent, where can we find this information, and all of that fun stuff. So, for starters, we are starting with the graph below that shows the height of a baseball as it flies through the air after it was hit by a baseball player. Right, so it has this nice parabolic arch. Before I even look at the graph itself, I want to point out a couple of key features that the graph has. First of all, beautiful title. The title tells us exactly what we're looking at. We're looking at the height versus the time for a baseball. Okay, the height is our dependent variable. It is found on the y-axis, and time is our independent variable. It is found on our x-axis. Both of those values have units, so we know that if we are somewhere here, that is at 2 seconds, right? Our height has the units in meters. We also have some key points labeled for us, so we know what those values are. Instead of just guessing them. So when we have our characteristic points, like our x-intercept, our y-intercept, all of that jazz, we can see what they are very clearly. Okay, so that is a very great graph, and we are thankful for it. So what we're going to do for starters is we are going to determine the following characteristics of the graph, and we're just going to round to 2 decimal places here. Okay, so for starters, the first one says, what's the vertex? So we know that the vertex occurs where the graph changes direction, which is right up there. And the vertex would then be 2.55, 32.34, because we're rounding to 2 decimal places. Our x-intercept, notice here, if we zoom in, we don't have an x-intercept there. It continues into the negative realm, but the negative realm doesn't make sense if we're talking about time. So we only have one x-intercept, and that would be 5.12, 0, or we could say x is equal to 5.12. Our y-intercept is 0, 0.45, or we could say y is equal to 0.45. The maximum height of the ball, remember that the maximum occurs at the vertex, and we're talking about the height, which is our y-coordinate. So our maximum height is 32.34 meters. The time of the flight, so how long did that ball go through the air and before it hit the ground? Well, we scroll back up here. It was hit, it's in the air, 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 ground. So that whole amount of time will be represented by our x-intercept there, which means it was in the air for 5.12 seconds. Lastly, the height of the ball when it was struck by the bat. Well, it was struck by the bat when the time was equal to 0. And our time equal to 0 means our x coordinate is 0, which means we have our y-intercept. And the ball wasn't hit off the ground, right? Because if you play baseball, you're hitting a pitch. And it was hit, or the height of the ball when it was hit was 0.45 meters from the ground. Now, these are all key points that we can see directly on the graph super clearly. Those are the points that were labeled. We could also use the graph to estimate some of the following things. So, I'm going to just zoom out so we could maybe see both of them at once. So, we're going to use the graph above to estimate the following. So, the height of the ball after 2 seconds. So, we want to find the height after 2 seconds. So 2 seconds would be somewhere up here. And we're looking for the height of the ball at 2 seconds. So with that being said, I'm just going to erase this. we want to find the height here. And we're estimating. So it doesn't have to be perfect. We know it's between 30 and 35. It's closer to 30 than it is 35. We might say, I don't know, when x is equal to 2, our time is equal to 2, our y is maybe 31. So the height of the ball could be 31 meters. Okay. Now the next thing it asks is the time the ball was 30 meters above the ground. Okay, so I'm just going to erase what we did for the last little bit of work. So the time the ball was 30 meters above the ground. Well, let's see when the ball was 30 meters above the ground. So the ball was above 30 meters for the amount of time from here when it reached 30 meters to here when it got to 30 meters. So for this amount of time. Okay, because the ball was above 30 meters, above 30 meters, above 30 meters, hit it and went back down. So to think about it, when did the ball get up to 30 meters and when did it get back down? We can say, well, when y is equal to 30 meters, one of the x values was 1.8 seconds-ish, right? We're estimating here, so it doesn't have to be perfect. And the other one was when x was, I don't know, maybe 3.25. It kind of looks like it's a quarter of the way. Maybe it's a little bit more. It doesn't have to be perfect as long as it's close-ish. So the time the ball, it didn't say above 30 meters. It was just 30 meters above the ground. So the ball was 30 meters above the ground at 1.8 seconds and 3.25 seconds. And last question says the time the ball was 35 meters above the ground. Well, 35 is here. And the ball never reaches that point. So we're looking for when y is 35 meters or higher. And that never happens. So that never happens, which means how long was it 30 meters or higher? Well, for 0 seconds. All right. So that's what we could use a graph for to make some estimations. We could also use the graph to figure out exact answers to questions by using the characteristic points. Another thing that we might be asked to do is we might be given the equation itself, we might be asked to graph it, and then figure out the same questions as we did before. But if we're asked to graph it, we're going to be using Desmos to help us with that. But a couple of things about graphing before we even get started in reading the question and things like that. A graph must include the following. So we must have a meaningful title. We must have labeled axis and units. We should have a consistent scale on each of the two axes. So they don't have to be the same scale. Like if x is going up by 1, y could go up by 10 if it wanted to. But it should be consistent. So if we're going up by 1, every one that we go up by should be around the same length. Okay, and I can show you what that means when we're doing this question together. And the graph must fill the space provided. So we don't want to squish it into the small little corner of the space. We want to kind of fill it out as best as possible. Alrighty. So we are going to take a look at this question. A batter hits a pitched baseball with a bat. So similar scenario. The ball was 0.5 meters above the ground when struck. The function which represents the height of the ball measured in meters as a function of time recorded in seconds is below. So we have h of t is equal to negative 4.9t squared plus 20t plus 0.5. So using Desmos, we're going to go ahead and plug this into Desmos to figure out our graph. Negative 4.9 x squared plus 20x plus 0.5. And I'm going to change this just a little bit, just so that we can kind of see that more spread out. So this is what our graph is going to look like. Keep in mind that it doesn't make sense to have negative height, and it doesn't make sense to have negative time, right? So we aren't going to draw all 4 quadrants of the graph. We're just going to be drawing what we see on Desmos here, okay? I will zoom out though so that we can see some characteristic points so that we can help follow along. But before we even do that, we're going to go ahead and start making some good label decisions on our graph. So first of all, we need a title. We want to talk about the height of the ball over a period of time. So the height of the ball over time. We want to always, in our title, relate both variables together, our x and our y variables together. Okay. What is our independent variable? Well, of course, that is time. Time happens regardless of height. So time will go on our x-axis, and our time is in seconds. So we need to make sure we have time and our units in seconds. Height is our dependent because the height of the ball depends on how long ago it was hit, and our height here is in meters. All right, next we are in charge of creating a scale. So our x-axis, our time, is going to go from 0 all the way to 4.106. So we might want to go from 0 to 5, right? And we want to make sure it's spread out. So we're not going 0, 1, 2, 3, 4, 5, because what it says in our instructions here is that we want to fill the space provided. So we don't want to just cram things into a corner. That's actually where you could lose communication errors or little half marks, is if things aren't drawn clearly, especially if you're providing or you're being provided a big space. You want to make sure you fill it as best as possible. So we are going to go up. And maybe it's smart to go up by ones. Maybe that's might be what you have. So 1, 2, 3, 4, 5. Okay. Something that you shouldn't do, I'll do it in pink here. So if you go up by 1 here, and then this is 2, and that's 3, and this is 4, and this is 5, this is not a consistent scale because the space between each of those numbers is not the same. So when it says consistent scale, it doesn't mean that both the scales on the x and y axis have to be the same. It just means that if you're going up by ones, each space between each one you're going up by should be fairly consistent. Alrighty. On our y-axis, our maximum height is 20.908. So maybe we want to go up by 5s and then go from 0 to 25 if possible. And this might take a couple times, so always try in pencil. So 5, 10, 15, no, that's a little bit too low. 15, 20, 25. That's not too bad. 0, 5, 10, 15, 20, 25. Okay, and my recommendation is always to do your scale in pencil, because if you mess up, you can easily erase it and try a new scale. But the consistency in the scale is super important, so make sure that you are taking your time to be close to accurate as possible. All right. At this point in time, we can graph our points. So when we're graphing, we should have at least our characteristic points here. So the 3 that are currently labeled on Desmos. Currently labeled on Desmos will do. So we start with 0 and 0.5. 0 and 0.5. So 0, 0.5. And we want to label them as we go too. Our next point, our maximum, occurs at 2.041. So ish. Here and 21. Ish. So we have 2.041, comma, 20.908. And we hit back down at 4.106. So 4.106, comma, 0. When we are going to go ahead and graph this, we are going to draw a smooth curve. If it's not smooth, it's all bumpy and lumpy, we're going to erase it and try it again. Alrighty, and this is what our graph should look like. So, just to double check to things that we've included on our graph, we have a meaningful title. It relates both our variables together. We have labeled axes with units, which is awesome. We have a consistent scale. So consistent, remember, doesn't mean that if x goes up by 1, y has to go up by 1. It just means x is going up by a consistent space between values, and y is going up with a consistent space between values as well. And we used the space provided. We didn't squish it into some tiny little corner that we can barely see. So this is going to be important. All right. From here, we can determine all of this information. And we can use Desmos to determine that information too. We don't have to use our graph, although it represents the same thing. But Desmos allows us to make sure that we get the exact value. We're not estimating anymore. As soon as we're given the equation, we're able to figure out exact values. So we are going to answer all of this with 2 decimal points. So for our vertex, we could see on Desmos, but we could also see in our graph, we have 2.04, comma, 20.91. Our x-intercept, again, we could see on Desmos, as well as our graph, we have x is equal to 4.11, or 4.11, comma, 0. Okay. Our y-intercept, we could see is y is equal to 0.5, or we could go 0, comma, 0.5. The maximum height of the ball, again, we could see that at our vertex, and that would be at 20.91 meters. The time of the flight, well, that's when we hit our x-intercept there, and that's a total of 4.11 seconds. And the height of the ball when it was struck by the bat, well, that was 0.5 meters, because that is our y-intercept there. Now, this is the part where we actually don't need to do any estimating for anymore. The height of the ball after 3 seconds, well, when x is 3, that's when we're trying to find the height or y value. So in Desmos, all we're going to do is we're going to go x is equal to 3. And we can find that exact intersect on our graph. So when we have x is equal to 3, our y is 16.4, which means after 3 seconds, our height is 16.4 meters. So h is the time at which the ball was exactly 10 meters above the ground. So our height of 10 meters is when y is equal to 10. We can plug y is equal to 10 into Desmos and figure out it happened twice. It happened at 0.55 seconds, and it happened again at 3.54 seconds. So 0.55 seconds and 3.54 seconds. And lastly, the time the ball was 25 meters above the ground, well, that would be when y is 25. We want to figure out what x is. So when y is equal to 25, and we can see that never reaches. So the ball never reaches that height. So 0 seconds. Alrighty, so when we're given the equation, the difference is we don't have to estimate. We can go ahead and use Desmos to figure out our exact answers. Alright, last question of the unit. Whoop, whoop. Is we have a skier's jump was recorded in frame-by-frame analysis and placed in on the picture as shown below. The skier's coach used the picture to determine the quadratic function that relates the skier's height above the ground, y, measure in meters, to the time, x, in seconds that the skier was in the air. So we have this function here. And we're going to round all of our final answers to 2 decimal places. So let's start things off by going ahead and plugging in that graph into Desmos. So we have y is equal to negative 5.9 x squared plus 15x plus 1. And we might want to zoom in appropriately. If you're having a hard time zooming, you could actually manually set it. So for example, if you hit this little wrench here, you could say, well, I want to see my x-axis from negative 1 all the way to, 5. And your y-axis, you could say, well, I want to go from negative 1 to, I don't know how high skiers jump. You can say 10. And you go, okay, well, from here I could pinch and zoom as you need, or you could adjust it. So you could say, I think I don't need to go as far my x. Maybe I only have to go to 3. So instead of going to 5, I could go to 3. And then so that it could kind of fill the space if needed. So you could use the wrench tool, but you could also pinch and zoom to get a better idea. Alrighty. The first question says determine the vertex. And we could see the vertex has the coordinate point 1.27, because we're rounding to 2 decimal places, comma, 10.53. Well, what is the skier's maximum height? Well, the maximum occurs at the y value of the vertex. So the max height is going to be 10.53 meters. Well, after how many seconds did the skier reach the maximum height? Well, that's just, of course, the x value at my vertex when I reach that maximum. So after how many seconds? After 1.27 seconds. Determine the x-intercept of the function. Well, we could see that is 2.61, 0. How long did it take for the skier to reach the ground? Well, that's my x-coordinate at my x-intercept. So it took 2.61 seconds. State the domain of the situation above. Okay, so notice that our domain does not extend into the negatives, right? Because we can't have negative height and negative time. So we are just seeing this value here. For our domain, our time starts at 0 and continues until I hit the ground, 2.61. And they're both included, so we use hard brackets. In set notation, that would look like x such that, or the set of all x such that 0 is less than or equal to x, which is less than or equal to 2.61, and x is an element of the reals. For my range, I'm looking at my height. My minimum height is 0, and that's an included value, and my maximum height is 10.53, and that's included as well. In set notation, I have the set of all y such that 0 is less than or equal to y, which is less than or equal to 10.53, and y is an element of the reals. And that is it. That is my domain, that is my range, that is my unit. So we are actually all done for chapter 7. There is some homework that I'd like you to go and give a shot. You are able to use Desmos for everything. Remember, that is a tool that you are able to use. Other than that, have an absolutely wonderful day and chat with you soon. Bye!